Muted.
I would like to get started. Today's presentation is on performance modeling and rapid system exploration. What we're going to do is we're going to first discuss the different applications of VisualSim Architect. Today's discussion is really focused on performance analysis and system exploration. If this is not exactly the application we're looking for, send us an email and we'll make sure that we can answer some of your questions. We have webinars every other week and we try to cover as many of the applications of VisualSim as we can. The main items we're going to cover today is timing and power analysis. We're looking at architecting hardware, software, and the network architecture. We're also going to look at an end-to-end design of your power system, right from generation, storage, management, and consumption. And finally, we're going to look at an early visual demonstrator that you can utilize to be able to attach to your proposals, or even for some early demonstrations for certification or for other customer applications. A quick introduction to Mirabilis Design. We were founded in 2003 and we're based in Sunnyvale, California. We have offices in various parts of the world, including support centers. Our market is pretty diverse in that we have customers in over a dozen application areas, including aerospace, automotive, multimedia, consumer electronics, and semiconductor. The goal of Mirabilis Design is to really ensure that you create the right configuration to match your customer requirements. A quick introduction to VisualSim. VisualSim is our main product. It consists of a high-performance discrete event simulator, enables graphical and hierarchical modeling, and what really makes VisualSim stand out is the extensive libraries that allow you to be able to construct models for a variety of applications. Even today, you're going to see something like about 6 or 7 different applications of VisualSim Architect. We have 2 types of libraries. We have a generic library that can be utilized for a variety of purposes, anything from building a toll road network to business analysis to hardware stochastic modeling, to looking at very specific today hardware, software, RTOS, and networking components. We're going to also show you some of our analysis, debugging, and virtual prototyping solutions so you can see how the system model can be extended beyond its existing scope to use it for sales and marketing purposes as well. Today's focus is going to be about system exploration, which consists of power, performance, and functionality. What are the areas that VisualSim really plays a major role? First and foremost is in assembling up your proposals, ensuring that your proposal meets all the requirements, looking at project feasibility. Now, once you win the proposal, you want to look at sizing the system, generating the specification, providing the golden reference for your implementation to verify that and validate that the implementation meets the requirements. Also looking at scalability and future construction by seeing what how much can you add to an existing architecture. All of this is going to be built around cost, timing, and power consumption. A quick look at something that I mentioned earlier, which is our system modeling IP. As you can see, we have a large array of modeling components that can be utilized very quickly in assembling up your system. Most of these components are described on our website, but if you'd like more information, you can always contact one of our application engineers, either today or via email. One of the key things in VisualSim is that we have 2 parts to our system. The left-hand side is where the architects are constructing the models doing failure analysis, reliability analysis, doing use case studies, exploring the various options available for different use cases or different workloads. Now, once this has been completed, a specification is generated, golden references are also generated. Then on the right-hand side, we provide you a platform where you can exhibit the models to be able to use as demonstration, either for the proposal or for communication with partners and with other parts of the organization. Now, moving away from the presentation, I'm going to show you a quick introduction. So this is the block diagram that is generated out of a model in VisualSim. As you can see over here, if I can run my mouse over any of the blocks, what you will notice is all the parameters and all the attributes associated with it. I can always click on any of the blocks and it will take me into the internal details of that particular component as well. So you can actually track all of it. Now, this is what we call the static part of our documentation. So all the documentation that you have in your model is all executed as part of this thing, and it's all generated for use, for others to use apart from the architect themselves. In addition to that, right from within the browser, by the way, this model is being run right out of Florida, you can click on this launch button. When you click on the launch button, it actually opens up a model that was created originally on the desktop right from within the web browser. What this allows you to do is actually allows you to run the simulation right within your web browser. So you can actually view the exact same model, you can double click on it, you can change any attributes, you can click on the go button and actually run a complete simulation right from within the browser. So how does this help? It allows you to take the model and use it as your communication tool very, very, very early in the design process. So even though your product lifecycle may be, or your development lifecycle may be 5 years, within the first 6 months, you could have something that would emulate exactly what your final product is going to look like. As I mentioned, there's always engineers standing by to answer any of your questions, so feel free to ask any questions and we'll be happy to answer all of them. Now, let's break it down and look into different aspects of VisualSim application. The first is more of a generic time-based, so anything that changes with regards to time, and the attributes of interest should be resources, usage, and traffic. So what you're trying to do is you're trying to run use cases to evaluate the expected behavior, analyze how things change over time, what are the resources available, what's the consumption, what's the allocation mechanism. Out of this, we generate statistics and user profiles. At this point, what I'm going to do is move over to VisualSim Architect, and I'm going to open up a particular model. So this was a model that was originally constructed in SystemL and AADL, and what we're doing is we're converting this into a VisualSim model complete with a hardware platform that can implement this architecture. So we're going to talk about this particular example in a follow-on slide, but I wanted to give you an idea of what it is that you can do. You can define the behaviors, which can be very generic. It doesn't have to be hardware, it doesn't have to be business, or can be any combination of those. And once you assemble them, you can use a process called mapping to define exactly how it's going to be implemented. And then you can click on the go button and you can run simulations to exactly view how the implementation is going to be handling this particular use case or this particular system. So in this case, if I look at this model, what I have is that this is a toll road project. So I've got vehicles coming in, checking to see if the road is closed or open. If it is, there is an, right from here, there's an entry camera that takes a picture, that checks each and every entering vehicle, checks the car numbers, and then as it continues and reaches the exit of the toll road, takes another picture. So what we do is we look at congestion control, we look at the mean speed, and what we're doing is all of the activities that are executing are actually handled in the hardware platform right over here. In this case, we're using a very specialized platform that is that provides you the all the capabilities on a single set of boards. Now, when I look at the analysis output, it shows me how much of MIPS I'm getting on my processor, what was the latency, how much power was being consumed in the system, how much was the congestion. So you can see how the congestion is changing over time. So this was actually where the algorithm or the functionality is also being executed. Here what you're looking at is you're looking at the instantaneous, and the red one is the average power. So what that means is you're looking at how much is the peak power consumed by all the hardware systems that you have there. Now, in addition to that, there are certain other functions, items, like for example, the road gets blocked. So think about this as a failure scenario, so which means the drivers have to take an alternate path. So allows you to experiment with these kind of situations to see not just what happens in a regular situation, but also what happens when there's a failure or when there is some obstruction in the activity. Now, from taking a very generic system, let's get to something very specific, hardware system. So one of the things in the system flow that VisualSim does is really connect the very high level behavioral description in a SystemL to the hardware software mapping of how it needs to be implemented. And as a return path, provide the requirements back to systems engineering, and on the implementation path, provide the golden reference for doing validation and for the specification as well. So what this is really an end product study. This is what the final product is going to be look like when it's deployed at the customer's location. So one of the things you want to do is you want to be able to run a lot of corner cases, run use cases, workload analysis, be able to identify any bottlenecks or system failures. And the key attributes that you look at would be latency and power consumption. So for example, we're looking here at a SystemL diagram where we're evaluating this, the toll road example that I was showing you earlier. So you can see this is the main definition right over here, where you have the vehicle details and then you have the details of the actual system that's implementing it as well. Now, you just saw the VisualSim model, which took this and implemented the behavior of these two, but in addition to that, it also mapped it to a real hardware platform, so it could actually take the combination and look at which attributes are implemented in hardware, which attributes are implemented in software. Once you're happy with looking at the entire end-to-end system, you can then start looking at specific details or specific subcomponents. So in this case, you may look at like the software, you may look at the power consumption, or the power management modules, or you may look at the RTOS. I'm just going to move over to VisualSim at this point, so we can take a look at a few examples. So we're going to take the first example we're looking at is a complete end-to-end control system. So what we have is we have a variety of controls, which is this is a computer, a vision control based robotic arm that is cleaning the nuclear power plant. So you can see we have the vision, the remote sensor, the servo, sonar, and communication systems. We've got the work stack and the power information. These really trigger the system behavior. So this is what we're going to be implementing in the subsystem in software. So when I go into details of this one, you can see it's a finite state machine, and when I go into further details, you can see exactly there's the auto navigation or a manual navigation in it. and then perform activity. So using this, you can essentially describe your software either in the form of a script or in form of a control right over here. So what can you use this model for? First is you can use the model for is to see how much time does it take to complete certain activities or certain tasks. So you can look at the associated timing. The second attribute that you can look at is you can look at what was the power consumption, what was the energy consumed. The third attribute that you can look at is you can look at the usage of each different resource. So each different control component. You can see how active they are and how does it help you? One is it helps you from a standpoint of can I reduce the power consumption just using software. If these are my hardware controls of servo motors and different MEMS systems, what do I need to do in terms of how what should be the specific component I utilize in terms of the the rate, the clock speeds, and different kinds of attributes such as those. In addition to that, what also gives you is you can look at attributes such as the clock speed of the processor, the memory, and other such hardware systems. So what this allows you to do is allows you to look at the software implementation of your system and understand how it's going to be behaving on a certain target hardware platform. In addition to that, what you can also do is you can look at the overall end-to-end system. So for example, over here, this shows me my generation. So I can use like a motor, a wind turbine, or I can use like a more solar panel based or or something that's more an existing system getting a trace file input. Any of those kind of, or could you just be like a regular power socket? Connect it up to a battery, and the battery has all the attributes. You can select what type of battery you want, what's the battery profile, what is the charge profile of the battery, ambient temperature, all of those kind of attributes. And then of course you can start assembling up your actual system. You can add your details of what the power management is, what is the consumption, and finally look at what your overall end-to-end power system is going to look like. I could take something like this, and I could be looking at something that's far more complicated such as this, which is an entire cube stack. So you can see all the different subsystems that are located in the cube stack. You can look at the battery, the photovoltaic array, and then these are the use cases that are defined for this particular satellite system. So when I run a simulation of this particular design, I can look at what is the time it took to complete different tasks in my system. Look at how things change as a result of being in discharge or charging mode. Looking at the subsystem activities, looking at the what is the energy consumption of each of those different subsystems in my particular design and stuff. Another aspect of VisualSim, so we looked at entirely a business process system, and we looked at a subsystem, but you can also use VisualSim down to a chip level evaluation. So you're designing a processor, an FPGA, an SoC, or an ASIC. Allows you to explore how that particular system is going to be, or that semiconductor device can behave in the context of the full system. So you can look at what's the reliability aspect, what's the power consumption, looking at all of those kind of attributes. Now moving back into VisualSim and taking a look at a model here. There you go. So here is a system where we got an ARM-based architecture. If you notice, every design we've been looking so far has a different processor platform. So you have, we had a PowerPC, we had Intel, now we've got an ARM-based platform. So if you look over here, And if I look at this thing, you can see it's got a coprocessor, it's got some internal buses, bridges, memory, it's got a hardware accelerator board. So you can look at, in this particular case, I've got a multimedia application where I'm looking at some image algorithms that I want to implement in my hardware platform. And I want to see how many images can I implement or how many images can I process with this particular target application over a period of time, in this case, 20 milliseconds. The goal is we want to get it to over 13,000, but we want to keep the power consumption down below certain limits. So as you can see over here, based on a completely software implementation, we can only get to about 6,600 frames per second for that period of time. Power consumption is fairly good. It's only about 1 watt of power for this particular chip. Now what I'm going to do is I'm going to take parts of these and decide to implement them completely in hardware. So I'm going to just modify this parameter over here, and I'm going to go ahead and rerun the simulation. So what's going to change now is you're going to notice that this hardware platform is starting to get some power values. Earlier on it was 0. But what it also did was it modified the power profile. So which meant that the original power profile was no longer valid. But what happened was we could get it up to 14,000 video frames in that 20 millisecond time frame. But unfortunately, what you can see is the hardware platform is the one that's consuming most of the power load. So using this, you can do a power performance trade-off to come up with exactly what your implementation needs to look like. As always, if you have any questions, feel free to ask them. There's always engineers standing by to answer them, or I'll try to cover it during my presentation as well. Now, another aspect of VisualSim that provides a kind of a complete coverage over the design is really looking at the software. Now, one of the key attributes of software is that there's always a deadline within which the software task has to complete. Now, there are certain attributes in your hardware platform, like you're looking at the power consumption, the service latency, throughput, the reliability. All of them cause certain overhead to be set up into your system. So some of them can be in the form of diagnostics, some of them can be in the form of priority, some of them can be in the form of preemption. So what we want to do is look at every one of these tasks to figure out when do they actually complete. So for example, this particular task T3 was to have completed at about 230 seconds, ended up taking 300 seconds. Why? Had nothing to do with T3. In reality, there was a higher priority task that showed up right at 200 that started executing before T3 could execute. As a result of which T3 was preempted and waiting until it would complete down here at 300. So which means it took about 50 milliseconds of extra time over what was predicted or what was required, which is your task deadline. So using this, you can try to analyze where is my system bottleneck. What is causing my my system to not be able to deliver the functionality that we're looking for. So moving over to another demonstration in VisualSim. We're going to look at implementation of a particular of a particular operating system and the how that is actually behaving. So for here we have a lot of schedulers. We have 1, 2, 3 schedulers, and they're all running independently, but they're running concurrently. So think of them as time-space partitions. And you can actually see that these are the different tasks that are executing. These ones over here, including these COM tasks. And you can see over time, which one's executing at what instance. So I'm going to actually zoom into this region over here. So you can see some of these tasks, like for example, this T1R4 was supposed to be executing right at this trigger point of T4 right over here. I'm sorry, T1 right over here. But there was already a T4 task that was executing that hadn't completed. And then there was the R3 task, and then R4 executed. Now, what was already happening was that we've got this T2 task here that was really an extended task that delayed the T3, the T2R6, and the T1R1. All these tasks are delayed because of this extended task that occurred because of a timer, of an interrupt. And these are things that, when you run the simulation model, you can actually capture. Now, one of the things you can do with this one is you can set up a variety of attributes for the operating system as well. So, for example, you can set up the timing for the different tasks, or you can inject faults into the system. The faults will help you create different scenarios and see whether your, for example, in this particular case, where the operating system is able to handle the safety critical tests like an ISO 26262. You can also set up different types of test mechanisms, like check to see if a certain checkpoint executed a certain number of times, or you can see whether they all implemented in a certain flow order. So you can set up a variety of test cases to validate that my entire software is behaving correctly. The purpose of doing that can also be for early certification data. Now, moving back to the presentation, modeling software. So software tasks are really modeled with 4 different attributes: reading the data, getting certain resources, which is, if either a resource gets preempted or if a semaphore that says, I need, once I get access to it, I can start executing. The actual execution of processor, and then once I'm done, writing back the data. There's always other attributes associated with that, like, for example, messaging and interrupts and events and timers and things like that. A lot of it is handled by the RTOS itself. So in this case, for example, I got a low power mode, there's a wake up and pre-processing, the sleep, and then there's like advertise, there's the actual transmit and acknowledge. So the operating system can be doing a variety of activities, or it can be that it can be triggering a lot of control activities as well. Now, the actual algorithm or the actual task sequence can be expressed either in terms of a state machine, like I showed you with the control for the computer vision, or it can be done using a script, or it can be a statistical trace file. The statistical trace file can be where you can generate an instruction trace from your existing system and use it, or you can generate a statistical trace using some of our internal behavior tools as well. The software behavior essentially is recreating the flow diagram you would have in a UML, SystemL, or AADL, or in tools like MatLab and Simulink. Now, what are the types of analysis? One is, what is the message passing mechanism? Are you able to meet the deadlines either because, the network connections is too slow or it has lower priority? You can look at multi-core, multi-processor type effects. How do you partition it across the multi-core? If there's issues of cache coherency, how do you handle that, and how does that impact the effective throughput you get out of the memory? What are the things you can do? You can look at how you migrate your existing software that might be a single thread to a multi-threaded architecture. You can look at extending the software, running it at a higher clock rate to see what the performance looks like. So there's a variety of software design analysis. If you look at the progression where we're going, we started off with a more of a business type process, moved to a full system, subsystems, semiconductor level. Now we're looking at the software aspect as well. Now, a final aspect of the system is really the power. We look at power as an offshoot in almost every single design. What the power was really doing was looking at what was the dynamic power. You know, in today's design, most times when you look at the power generation or the power storage, you're spending all your effort in trying to create Excel spreadsheets that give you a certain information about the power. What that means is that it's giving you a very average term for the power. So for example, when we started off, this was the starting point in that model that you saw for the power consumption, which kind of matched the average power you generate. So you take all these numbers and divide it by 4 and you get an average number. So that's kind of what you use for every one of the use cases. But here, because the dynamic nature, things get turned on, turned off, things like that, the power consumption actually changes. The power profile completely changes. And this is kind of the important thing that we look at in VisualSim, which is really the dynamic state-based power. Look at the peak, instantaneous, and the average power. We set a power for each device, each state, and also for each task. So you look at the effect of transition between different states and the time that it takes to be in a single state before you want to transition out of that. You can also incorporate the battery effect. You can look at like the peak loading in the battery. You can look at like, for example, what happens in the event of a thermal shock to the battery life. It is a 10-year life guaranteed battery. What happens if you have thermal shocks or too many power spikes or current spikes? What is the life of the battery? Evaluate all of those. So all those can be done using a single platform of VisualSim Check. So you're looking at the end-to-end energy analysis. So you got your user use case profile, the photovoltaic cells, the batteries, the loads, the power management, all of these to generate out your power profile. So you look at your discharge and you look at your lifetime energy consumption as well. So this is now looking at it purely on the power base. You can also create complex state machines. The purpose for creating the state machines is to enable you to be able to explore different power management algorithms. So for example, what do you do when your satellite is facing the sun versus when it's in an eclipse? Or for example, I'm now in auxiliary power. What are the devices do I keep turned on? What are the devices do I turn on? Looking at also the communication aspect. So I have my communication transmitter receivers. So when I'm transmitting, do I turn off all the other storage and processing related activities? So that way I can conserve my power better. How do you do power performance trade-off? We looked at it very briefly, but really it consists of 3 parts. You have your architecture, which is your hardware software platform, the behavior, which is what essentially is your flow diagram of your system, be it in hardware or in software, and the final one is your power spreadsheet that you can then feed. So you can look at anything from utilization of your buses to your cumulative power analysis. So gives you a complete vision of your full system, be it a semiconductor or be it like we showed you at the toll road, which is a complete end-to-end system which is highly distributed across many miles. When you want to get more detailed information, especially when you're trying to debug it or you want to try to provide a golden reference, we provide you very detailed timing diagrams, instantaneous values, so you can kind of track where your system bottleneck is or where my excessive power consumption is, how I can shift my offsets for my software so I can reduce the power consumption, things like that. From a pure semiconductor standpoint, you can actually run what's called a cycle accurate analysis, which means I can run clock by clock by clock, essentially what is happening inside my semiconductor system as well. So you can go from a full system all the way down to just a bit of a semiconductor piece where you can run a cycle accurate implementation of it. These kind of accuracy would match exactly what you will see in your Verilog or even when you do your hardware testing. And as you can see, you can get your timing diagrams down to, you're activating your LPDDR bank activities, your writes into the bank, and then also all the refreshes. So you can actually capture very, very detailed power information. So you can see what the instantaneous and the red one, which is your average power as well. At this point, if there's any questions, feel free to ask them on the chat panel. There are engineers standing by to answer these questions for you. Moving on to the last aspect of today's presentation that I'll be covering, which is related to network simulation. So one of the things in today's systems is that it's not just sufficient to be able to just look at a particular subsystem or look at a full system, but rather you've got to look at a very extended system. So if you have a large number of IoT devices connected to a local hub that's connected to the to like a data center across multiple routers. What is end-to-end latency? What if I change the data sizes that I transmit? Can I reduce the power consumption of my IoT? Can I reduce the bandwidth that's consumed on my network? Looking at how much bandwidth I need to allocate for different applications. Also, for future reference, what happens when I add additional nodes, increase the number of messages? What happens if I add intermediate processing units? How does that impact my overall system behavior? Meaning, does it change my response time? Does it increase my battery life? Looking at those kind of attributes as well. From a network standpoint, I want to look at my application task latency, which is, do I keep all my sensor nodes in a small network of modules, or do I move them across, distribute them further across the network? What do I add? Start adding more and more capacity to my network. How does that impact my system? Looking at system simulation of such a design. Now, one of the things you'll notice in VisualSim is I've been taking on so many different applications, but I'm able to show you a demonstration right from within our tool. This is because we've got over 500 application examples available in VisualSim, and these can be utilized to be able to provide as a starting point for all my designs. So, for example, I could use this to explore, how much of, say I want to look at like the, like an entire aircraft. We've got a model of an entire aircraft. Say I want to look at a particular radar system. I've got a model of the radar. I want to look at a network of IoT devices like this one over here. I can look at this. Now, what is unique about this is I can also create failure modes. In this case, for example, I'm going to be removing a link and later on in the future adding the link. I'm going to look at the performance of this. So you can see what happens when initially I did not have a link. So at time 0, I removed a link, and then later on at time 150, I added the link. And you can, I'm sorry, the other way around. I had a link, and then later on at 150, I removed the link. So you can see rather than being distributed across multiple networks, it's now going through a single network link. You can see how much the latency changes. So for example, here I can generate the entire routing table, so I can see what's the usage or the bandwidth consumption in different network nodes and in different network links. Trying to see what happens when I change the network topology dynamically, or if I use a cognitive radio like a MANA type protocol, how does that impact my system? Now, talking about failure modes, there's a variety of failure modes that you can look at in VisualSim. So you can look at, like, for example, slow failures, which is, I keep losing maybe the number of coils in my generator, which means power doesn't just shut down, it slowly reduces. So over time, I can look at which devices do I keep turned on, which devices do I turn off, so that I can make a smooth landing. Or I can look at complete hardware failures, like say a board fails, or a connector fails, or a network link fails. How does my system continue to handle? We've had a lot of rocket customers that have actually done complete failure analysis of their entire flight control system. You can look at redundancy. So if you have triple redundancy, do you do the flow control by doing effective allocation across all the redundant boards, or do I just keep two boards always in reserve and just use a single board for my daily activity? Looking at software failures, so this is another aspect that I showed you a little bit earlier in the RTOS model, which is looking at failures in my software. Either the schedule table gets dynamically altered, or a value in memory gets changed. As a result of that, what happens? How does it impact the rest of the system? You can also look at deadline lapses, which means a few set of prior tasks are not able to complete within the deadline. How does that impact the future task? So you can look at all of this for like certification. So you can provide initial processing and communication data to the FAA or to other certification agencies to get approval, right? Even before you actually, even started development of the project, you can provide input as to what it is that you're going to be building, or what is your expected output, to see if there are any issues you need to address, which means your requirements could change, your specifications could change. All of those can be analyzed right up front while you're writing out the specification or even the project proposal phase. So looking at one of the scenarios that I was talking to you about earlier, where I have a lot of IoT devices or sensor devices connected to many hubs, and dynamically using MANET protocol, as these move around, they could be connecting to a different set of hubs. And then they go across a gateway of networks to get to an edge router that's connected to a server. So really what we're looking at is what's my end-to-end latency going from the device to the server and returning over time, as these devices keep moving around. So you can actually do these kind of analysis in your end-to-end system and incorporate all the different attributes, the hardware, software, the network, the power consumption, the any protocols, flow control, doing dynamic failure analysis. All of that can be incorporated into a single system model. And the reason we're able to do all of that is because we have a huge extent of library that allow you to construct all of them. Every single model you saw today was built using our basic building blocks. None of them required any custom development or any C programming or anything. So a lot of these models are things that you can create in a matter of days. So why invest in VisualSim and in system methodology? This was something that we did in conjunction with the customer. One of the things we noticed is many people do different types of model construction early in the design process. Just that it ends up taking a long period of time. One of the things, because a large number of libraries and very specific libraries to your system analysis that's available, you're able to cut short the model construction and spend a lot of time doing analysis, much more than the ones that you create with your more custom models. So as a result of that, you're able to do your communication and refinement much earlier in the design cycle. Today, many times you're doing your refinement while your implementation is happening, while in this case, you can actually do your refinement very, very early in the design process. So what we have seen in a large number of projects where we've done this type of analysis, with probably about 15, 20 projects, done these types of studies, we've been able to show that we've cut the implementation down by almost 20, in this case, almost like 20 to 40%. So that's kind of the range within which you can actually get more efficiency. So it can be to ensure your project schedule, maybe increase the revenue, maybe get early market timing. A whole lot of things can be done as a result of doing this upfront analysis. So with this, I would like to wrap up my presentation of VisualSim for performance modeling and rapid system exploration. If any of you have any questions, feel free to type them on our chat window, and we'll be happy to answer them for you.